Okay. Good afternoon. My name is Chukuma Ogbonnaya, and I'll be facilitating this session. I currently teach at University of Loughborough, Wolfson School of Mechanical, Electrical, and Manufacturing Engineering. I completed my PhD at the University of Manchester, where I focused on integrating photovoltaics and fuel cell for power generation. So what I'm going to deliver today is one of the themes that I discovered during my PhD, and I do sincerely hope that you will find it very useful. The title of this workshop is Computational Photovoltaics, and I want to use this opportunity to thank the director of Comrade Educational Services Limited for granting me the opportunity to deliver this workshop on their platform. I will tell you how you can get the codes through them if you need them. So we will roll like this today. The first thing is to contextualize photovoltaics. And we will now talk about model-based systems engineering. We'll talk about photovoltaic modeling and simulation codes. We then look at some case studies of how I apply the photovoltaic modeling and simulation codes. Then we can look at MATLAB simulation and how you can get the codes if you need them or if you ever need them in your research. We can have questions and then you can provide feedback to me. The first thing I want to say is that solar energy is the most sustainable form of renewable energy because it's everywhere, it's ubiquitous, and it's very clean and renewable. So having it everywhere across the globe and having it always with us makes it sustainable. So we can generate electricity sustainably from solar energy, particularly using technologies like photovoltaics. And we can see the intensive research ongoing in the area of photovoltaics, thermal photovoltaics, and integrated systems. We have been seeing some research focusing on how to improve the physics of the systems, how to enhance the efficiency of the systems, and how to integrate photovoltaics and thermal photovoltaic systems to other larger systems in form of distributed applications, and also integrating it to products like unmanned aerial vehicles, cars, electronics, and all of that. So I discovered that computational photovoltaics can really help researchers and developers to fast track development and improvement of photovoltaics. That's why this workshop was created, and I hope that we can continue the conversation. So let's contextualize the concept of computational photovoltaics. I define that as the use of computational programs, software, and algorithms to improve the physics, as well as aid the design and development of PV and TPV based technologies. So this is very, very important. It's all about how we use computational method to improve either the physics or the design or even the manufacturing of photovoltaics. So it spans the spectrum of the basic physics to application of PV system. Once we are using computational approach to do that, that's what I'm referring to as computational photovoltaics. let me also contextualize the concept of model-based systems engineering from the standard definition of International Council on Systems Engineering. Model-based system engineering is defined as a formalized application of modeling to support system requirements, design, analysis, verification, and validation activities, beginning in the conceptual design phase and continuing throughout development and later life cycle phases of the product. So you are not conducting experiments. Basically, you are using model-based approach to get information on the product and processes. Okay, so that doesn't mean that you're not going to use the information you get from the model-based systems engineering to feed into your experimental procedure. So it's a variable tool, and we can see from the benefits that it can help to reduce development costs. Imagine you want to experiment on, let's say from this diagram, integrated photovoltaic fuel cell system, and you must build the system first in order to investigate the system. That would be a costly venture. So in order to reduce the cost of developing integrated photovoltaic fuel cell system, you can use model-based approach to gain deeper understanding of the system before you even purchase any component of the system. So that is the benefit of model-based systems engineering. Another aspect is that it can save time. Model-based systems engineering saves time because you can investigate different scenarios and then reach a conclusion on the best scenario to take. Okay, so the next one is that it reduces technology risk. Model-based systems engineering can help you reduce technology risk. At times you want to create a system and you end up finding that the system is not sustainable. You can abandon it at that level instead of investing in the real components of the system, only to discover that the system will not be sustainable. So the risk of committing resources without being sure can be eliminated using model-based systems engineering. The other point is that model-based systems engineering can improve reusability of designs. So this is a situation where you can alter an existing design to innovate. So model-based approach actually increase the innovation space for engineers and scientists. Now, I want to bring the definition back to the topic, which is focusing on photovoltaics. This is a space where model-based systems engineering can be applicable in terms of photovoltaic research. Now, if you look at this diagram, you discover that at the center is a PV module. But we know that for you to create a PV module, you need to connect solar cells in series within the module. And for you to create a PV array, you need to connect the PV modules in parallel to create the module. So this photovoltaic, this model-based approach can actually help you to study systems based on photovoltaics, either by exploring it downstream or upstream. What do I mean by upstream and downstream? If you look at the PV, you can drill down to PV cells and you can model PV cells and study them in detail. You can also go deeper and begin to also explore the quantum level of photovoltaic cells, okay, up to the level of thinking about how do electrons move, how do you generate electrons, and how are they recombining within the system. If you go upstream, you can talk about modeling PV systems, like even PV farms, You can also think of integrating PV systems with other components like fuel cell and batteries and other components. You can also look at the integrating cost model to fundamental PV model. So you can explore different dimensions of PV systems or thermophotovoltaic system using model-based systems approach. I didn't forget thermodynamics aspect of it. So you can explore the energy and exergy models of thermophotovoltaic models. You can also perform parametric and sensitivity analysis of a PV model. So there is a whole lot you can do with a model-based approach. So still on the photovoltaic modeling and simulation code. This is a collection of code, up to 2,000 lines of code in MATLAB. So I systemized it, and I will tell you how you can get the codes later. The use of model-based systems engineering has to do with the problem you are trying to solve. We know that modeling cannot tell you all the information you need about a system. Modeling is just a tool that can help you to understand your systems better. So the problem you are trying to solve will actually determine how you are going to model the system and what you are going to be studying. So in this context, as you will see in the case studies, you can use numerical modeling, code-based modeling, model validation, simulation, parametric studies, and virtual experimentation. So including statistical analysis, systems analysis. So you can combine different approaches and methods to really take decision based on the evidence you are going to generate from your system modeling and simulation. So it's not something that there is a way of doing it, a standard way of doing it. What I'm trying to imply here is that your approach depends on the problem you are trying to solve. And that's where it gets interesting, because you can always create novel results by thinking creatively about your problem. So that's the point here. Now, let me just give you a kind of an overview of how you perform, how you use photovoltaic modeling and simulation code. Remember, I told you it's a set of codes I developed, and you can get them. First, you need to create the computational model of the system, of the physical system you are trying to model. Let's assume you want to experiment with a 100 watts PV model. The first thing you need to do is to create the 100 watt PV model. And once you create the code representing that physical system, the second thing you need to do is to validate whether the model actually represents the 100 watts PV model. So once you establish that the PV model is represented by that computational model, then you can now use your algorithm, okay, which will represent the experimental process if you were performing the experiment in the lab. So you now deploy that PV model you've created and validated under that experimental condition. You can hold some variables constant while you allow others to vary. Okay, so once you deploy it under that condition, you can then extract some variables from the modeling and then visualize it through plotting of the graph, and also, you know, comparing variables with variables, depending on what you want to find out. I want to show us this. This is a MATLAB code which represents a kind of basic PV model. Okay, so you can see how these codes, these formulas, were translated into codes. Okay, so this is not the comprehensive. I just extracted this as an example, so you can see how these equations were converted into code, MATLAB code. So if you want to model a PV module, you can use this code to create a PV model, and you can then select the parameters that will give you the actual watts you want to create. Remember that you have different parameters. For instance, the open circuit current, the number of cells, the type of solar cell. Is it silicon? Is it indium? Is it indium? Is it gallium arsenide? Depending on the PV cell you are modeling, okay? So the PV parameters depend on the type of PV module. And that's one thing that is very nice with this code-based modeling. It's a gray box approach. It's not a black box approach. You can see all the parameters and you can change any of them depending on the system you are modeling. Okay, so the next point I want to raise here is the problem that makes PV modeling somehow challenging, and that is the concept of transcendental equation. The transcendental nature of PV modeling makes it somehow difficult to use a straightforward way to model it. If you look at this equation here, you can see that if I ask you to solve this equation that y equals 200x y, I don't know, can somebody contribute? I want this to be interactive as well. What do you think? How do we solve this equation? Any idea? We can see that there is y here as the subject of the formula, but we also have y here at the end. So what do we do? How do we solve this type of equation? This is called a transcendental equation. This is, I published a paper on transcendental equation. You can download it, it's open access. You don't need to pay to download it. In mathematics, this is a title. So imagine you have, let's say, 5 other equations in addition to this single equation. So, and you are supposed to solve all of them simultaneously. You can see that it's going to pose a serious challenge. That is what the PV modeling also represents. It contains a transcendental equation, making it a system of transcendental equation. So what you can do is to use a method. One of the ways you can solve this equation is to, first of all, assume you are going to plot the graph of y against x. Okay, let's assume you are going to plot the graph of y against x. What you can do to generate your table is to, first of all, assume the value of y. Okay, once you assume the value of y, you can then find the value of x. You then assume another value of y, the second value of y, and compute the corresponding value of x. You keep doing that until you generate your table and then plot the graph of y against x. That's the only way to solve it. If you want to make y the subject of the formula, y will divide y and you have 1 equals 200x, and the y will vanish. Okay, so the only way to solve it is to solve it systematically. And you can see that computer has an effective means of executing such problem, because you can loop over y. You can say for y equals a range of value, solve this. Okay, the computer can first of all substitute a value for this, calculate that of x, substitute the second value, calculate for x, and keep doing that within the range you specified for the computer. Okay, so that's about that. Like I said, you can You can download this paper and read about how I propose that we can use to solve systems of transcendental equation. Even if it is not in photovoltaics, you can use my recommended approach to create your model, computational model, and then solve such equation. Having said that, I have another publication focusing on code-based modeling approach for photovoltaics, that's in solar energy. So basically, I have stated that you can model using computational approach, a PV cell, a PV model, an array, and large-scale photovoltaic systems. You can have a computational model representing such scales. So you can also perform parametric analysis of different parameters to see how those variables under consideration affect PV power generation. So code-based modeling approach also helps you to integrate new formulas within the PV model. So you can create your own formula. You will see examples of that. So let's look at this diagram. You can see that I connected 4 PV modules. The first one was just one. I connected the second one in parallel. You can see that it's increased. So each of them is 40 watts. So when you connect the second one, you can see the second one, red, is now 80. The next one is 120 and 160. So you can actually model a connection of PV models in parallel to create PV models. There are other ones, so if you want to read in full, also feel free to access this paper and read it from Solar Energy. The second one, which is very, very interesting, is how temperature affects PV generation. We know that temperature degrades the performance of PV systems. We can see the modeling, increasing the temperature from 298.15 to 313.15. You can see that the performance of the system degraded. We can see that the open circuit voltage is degrading, is decreasing. So these are the things you can investigate using a photovoltaic modeling approach. This is the third application case study of using this approach. This has to do with determining optimal location when you are faced with selecting a particular location to install your PV module compared to other locations. So you want to determine a location among several locations to install your PV module. I don't know. Looking at this diagram, can you guess which location will generate more? Some of us, can you look at this? This is this data is from Nigeria. We have Abuja data and Kano data, the temperature and solar cell, solar radiation data. By looking at it, where do you think PV generation per annum might be higher? Any comments? Yeah. Yeah, as expected, it's quite difficult to say, okay? It's quite difficult to look at data and say, yes, let me go and install a large-scale photovoltaic system in so place. So using this approach, a model and a system, an algorithm was developed to investigate which location among 6 locations across Nigeria. Nigeria is divided into 6 geopolitical zones. So one location was selected from each of the 6 geopolitical zones, and we simulated to investigate the location that will provide the highest amount of energy, the photovoltaic based energy. And let me show you what we found. So this is what we found. We found that the ranking is as follows. These are the locations used. We used Abuja, Calabar, Enugu, Gombe, Ikeja, and Kano. And I want to tell you that the data used for this study was 2 years. That's 731 days, approximately. So, as I said before, the first thing was to create the large-scale photovoltaic system. You can see here that this is 5 megawatts. So we first of all created a 5 megawatts and then deployed virtually these 5 megawatts in these 6 locations, okay? Because there must be a basis of comparison. So by deploying these 5 megawatts in these 6 locations is equivalent to trying to install these systems in these 5 locations, collecting data, and then comparing the data. That's what we mean by using model-based systems engineering to save time and save cost. By generating data, by using actual data to run this simulation, you can see clearly that based on the evidence that this location, which is Kano will generate more than Abuja. You can't determine that by just looking at the data, but you can use a model-based approach to determine that. So that's one of the, you can read, if you want to read this paper, you can read it, Journal of Cleaner Production. You can download it and read more about this. Another case study of how we used model-based systems engineering, use the method I'm discussing with you today is thermodynamics of PV-based generation, okay? And that paper is published in Journal of Energy Storage. You can also read about the research. Now, the question is this. We have a PV system, and we know that the PV system is a heat engine that converts solar energy into electrical energy. So from the first law of thermodynamics, we can see that we have fundamentally solar energy being converted into electricity or electrical energy and heat. Okay. Now, the first law of thermodynamics will not tell you about the losses being experienced in the system. If you now think about the second law of thermodynamics, which is entropy-based law, you can now talk about the Exergy efficiency of the system. And the Exergy is talking about the maximum theoretical efficiency of the system based on the environment where it is functioning or where it is being operated. So the Exergy efficiency of this electrolyzer. Now, the function of electrolyzer